So now to the big picture. How did Bohr get this? Okay, how was he able to, on paper and using theoretical models and algebra, how was he able to calculate the actual energy of these different energy levels in an atom? And using that, how was he able to actually explain the Balmer series that I described in my previous video? Well, Bohr made some postulates, and these are the postulates that we need to know and memorize for the exam. And the first thing that he said is that electrons will exist in quantized orbits, and those electrons don't radiate energy when they're in that stable orbit. They're able to just rotate or orbit in that way. Now that's strange because when an electron is orbiting, it's experiencing centripetal acceleration, so it should be radiating energy. But he said that they don't, and in order to explain that, he says that those electrons have to be explained through a wave particle duality. Maybe they have wave-like properties. And so before I talk about this part, what he could explain was that for these different orbits that have a circumference, they would have to fit a whole number of wavelengths around it in order to be able to form a standing wave. So 2 pi r, if I have a small radius, is equal to n lambda. And here I would have like one wavelength. The second orbit would have 2 full wavelengths in it. The third orbit would have 3 full wavelengths in it. And that would be some type of a model where each of these orbits are actually standing waves. And that would make sense that, like, if when we talked about with musical instruments, we have harmonics. Maybe these orbits relate to different standing waves inside of an atom. Okay, and then when he plays around with this equation and looks at the wavelength and says, okay, well, wavelength using the de Broglie equation, where Planck's constant divided by the momentum of the electron in that orbit, if I plug that in there, I can then rearrange this equation and I'll come up with this. So the last postulate that Bohr came up with is that the orbits are basically quantized forms of angular momentum. So when he rearranges his equation, MVR is the product of that would be angular momentum of these electrons. Well, the angular momentum in these different radii is the product of nh over 2 pi, where n is the number of the orbit, the shell. N is equal to 1, n equals to 2, 3, and so on and so on. So this was kind of Bohr's first claim to fame, and using this construct, he was able to then apply this relationship to a couple of different scenarios, and lo and behold, he was able to calculate this. And that's what we're going to be going for in the rest of this video. All right, so he uses creative algebra, okay? And in the first step of his creative algebra, all right, there's a couple things in here that are just unmeasurable. You know, if I wanted to calculate the energy of those electrons, there's two things I'll never be able to measure in an atom. I'll never be able to measure the velocity of the electron, and we can't get inside the atom to find the radius. So Bohr had to use some creative algebra, and he was thinking about, well, how would this electron orbit? Well, if I think about it in the particle level, I can think about it in terms of electrostatic forces, where the electrostatic attraction between the electron and the proton center is balanced by centripetal force. So he creates this mathematical relationship where this is Coulomb's law, and K is equal to 1 over 4 pi permittivity of free space. So if I substitute that into this equation, I'll go rather quickly. You can always pause it and try to figure out the algebra how I've done it. Well, after I've rearranged this, I have this formula over here. And if I want to find the radius of the orbit, I can isolate r, move that over, and I come up with this relationship. So the radius of each shell, each orbit, can be predicted using this simple relationship where E is the charge of an electron, 4 pi permittivity free space, the mass of an electron times the velocity squared. Only problem is we can't measure the velocity of those electrons. So we still can't calculate the radius, but if we were able to measure the velocity of that electron, then we would be able to calculate that radius. But Bohr went back to his original relationship, which helps him out a lot, and he was able to then say, well, I can measure the velocity of that electron. If I rearrange this equation, the velocity is going to be equal to nh over 2 pi mr. And then I can plug that value back in here to get rid of the velocity. And that's what he did. And so we're working through this derivation right now, where through a matter of cancellation, we get a value of r is equal to all of these constants. This is magic, okay? He was able to solve the radius using his postulate of angular momentum. He was able to solve for the radius at every shell, even though he doesn't know velocity. So that's kind of cool. This is how his wacky algebra gives him a bunch of constants that he can then put through to calculate the theoretical radius of different electrons. Now that he knows the radius, he's one step closer to calculating energy. And I'll show you the next part. So to calculate energy, he can look at the energy of an orbiting electron, just like we did with energy of orbiting satellites and whatnot. So the E total is equal to the kinetic energy plus the potential energy. Kinetic energy is 1/2 mv squared. Potential energy is electrostatic potential energy, which is here. Remember, this is R, not R squared, so that's potential, electrostatic potential energy. And again, he can't find velocity, but we had this. This is kind of cool. This showed up in one of the derivations over here. Where was that? Right here. Okay, so in his electrostatic forces and centripetal forces, he had that step, which he remembered. And then he can say, oh, mv squared is equal to that value. So then going back into here, he can substitute mv squared for that value. And those are the same. So then he can put that through, and he gets the total energy is equal to E squared over 8 pi E naught R. And he just found from what we did before this equation for R. So then if he plugs that value, if he plugs that value in for R, which we have over here, he's able to get this expression, which is a bunch of constants. And he can plug those constants in and be able to get the value of negative 13.6 electron volts over n squared. So this is what we talked about before. And this was Bohr's claim to fame, where he got his Nobel Prize, where he was actually able to, on paper, predict the total energy of every energy level, and using the calculations we did in topic 7, be able to predict the wavelengths for every energy transition.